Welcome to our next lecture in this series on condensed matter theory. In this lecture I want to talk about the Green's function of the midpoint of a one-dimensional infinite chain. And we'll take as a basis again a single S-like orbital. The Hamiltonian that we have is a sum of J is minus infinite to infinite, and we have an on-site energy of our particle. And we have an hopping between the nearest neighbor sites, j plus 1, and we can hop also from j to j plus 1. And what we want to calculate is the local Green's function, g creating and annihilating at site 0, which is given by the vacuum creating the particle at site 0, and then our propagator omega minus the Hamiltonian plus I0 plus, we annihilate it from site 0. So the expectation value that when you create a particle at site 0, sometime later it still sits at the same site, but now in Fourier space, so it's Fourier transform as a function of energy. And we will do this again with the methods that we discussed before in terms of continuous fractions. So our Hamiltonian looks like an infinite chain. We can label our sides 0, 1, 2, 3, minus 1, minus 2, minus 3, etc. We'll define the subspace A to contain site 0, and we'll define the subspace B to contain the rest. And we will be talking about B minus and B plus at some point for the states with negative index, and for states with positive index. And again, in our drawing, the circles represent sites with on-site energy. Epsilon s, and the lines represent hopping with strength as sigma. We can look at our Hamiltonian. The Hamiltonian in subspace A is just epsilon s, A dagger 0, A0. The Hamiltonian coupling A with B from B to A is SS sigma times, I can hop from 1 to 0, or I can hop from minus 1 to 0 to go from B to A. And then HB is given by the sum, J is 1 to infinite, epsilon s, A dagger J, AJ, plus A dagger minus J, A minus J, plus, and then we have the hopping terms, A dagger J, AJ plus 1, plus A dagger J plus 1, AJ, and now for the negative, A dagger J, AJ minus 1, minus J, plus A dagger minus J minus 1, A minus J. So we have a semi-infinite chain on the right, a semi-infinite chain on the left, and in the middle a single side to which we couple. And we want to know the Green's function of adding and removing a particle in the middle. So our Green's function can be expressed by an element of the Green's operator in matrix notation and we look at element 0, 0. Or if we write our Hamiltonian in terms of a block matrix, this is omega plus I0 plus minus the Hamiltonian for block A, decoupling from B to A or from A to B, and here the omega plus I0 plus minus HB, and then the inverse, and we are looking at element 0, 0, or AA, because of course A is exactly element 0. We can write this out. We have state 0, we create a particle, and then we annihilate it again, and you go back to the vacuum, and we have omega plus I0 plus minus the propagation in A, which is epsilon s, A dagger 0, A0, which is the Hamiltonian that governs the dynamics. And then we have the coupling from A to B, which is given here, and we'll put the SS sigma squared in the numerator, A dagger 0, A1 plus A dagger 0, A minus 1, A dagger 1, A0 plus A dagger minus 1, A0. And here is our coupling strength between subsystem A and subsystem B, divided by omega plus I0 plus minus HB. And again, we should realize that our creation and annihilation operators are matrices. Here A dagger A0 couples the Hilbert space A to the vacuum, and then A dagger minus 1 the vacuum to B, such that A dagger minus 1 A0 couples directly A to B. And then these are matrices of the respective dimensions. Now the dimension of Hilbert space A is 1, such that, well, A dagger 0 brings you to the vacuum, is a 1 by 1 matrix, the vacuum to A is a 1 by 1 matrix. So we can basically simplify this. And our Green's operator, or Green's function, for side 0 is given as omega plus I0 plus minus epsilon s minus, and here we have a particle in the vacuum, and then we go from Hilbert space A, and we have the vacuum, we create a particle to be in Hilbert space A, and you annihilate that from Hilbert space A, and these are all one-dimensional matrices. So we have here A1 minus A minus 1 as a sigma square divided by omega plus I0 plus minus AB, A dagger 1 plus A dagger minus 1 to the vacuum. So the propagation of our full Green's function is given by 1 over omega plus the propagation within Hilbert space A, which is of course very simple because it's a single side, and then the coupling by SS sigma to Hilbert space B. And now we should realize that our Hilbert space is given by a positive lead and a negative lead, and that you cannot hop from the positive leads to the negative leads. So when I create here a particle in 1, then I can never annihilate it from minus 1, I have to annihilate it from 1 again, because there is no hopping between the positive and negative indices. So we can write our Green's function as 1 over omega plus I0 plus minus epsilon s minus 0 A1 as a sigma squared divided by omega plus I0 plus minus the positive lead minus A minus 1 as a sigma squared omega plus I0 plus minus the negative lead. You either hop to the negative sides and then you have to hop back from the negative sides, or you hop to the positive sides and then you have to hop back from the positive sides. Well, what we have here is just SS sigma squared times the Green's functions of the endpoint of a semi-infinite chain. Yeah. B of Hilbert space B plus describes a semi-infinite chain, and you couple to side 1 for the first point, and that's exactly where you couple here. And the same is true for the leads at the negative indices. So we find that our Green's function is given by 1 over omega plus I0 plus minus epsilon s minus 2 SS sigma square times the Green's function of a semi-infinite chain. Well, the Green's function of the endpoint of a semi-infinite chain we did in the previous video. So using those results, we find that this is the square root of 1 over omega plus I0 plus minus epsilon s squared minus 4 SS sigma squared. And again, you have to be careful to take the branch cuts of your square root such that the imaginary part of your Green's function is 0 and your Green's function is Kramers-Kronig consistent, or the imaginary part or the real part falls off to 0 when omega goes to infinite. Now, in previous lectures we have also calculated this Green's function with the use of a Fourier transform. Our Green's function is fully periodic, so we can in principle look in k-space, and we know the dispersion, so we can calculate the local Green's function just as the Fourier transform of the Green's function in k-space. In the Green's function in k-space, your epsilon k is epsilon s minus 2 SS sigma cosine ka, where a is the spacing, and we have to sum over all points in the Brillouin zone. Now, of course, we want to take the number of states in our Brillouin zone n to infinite, which then means that we have to replace our finite sum by an integral minus pi to pi, and here you get the volume element in there, omega plus I0 plus minus epsilon s minus 2 SS sigma cosine k dk. And I already changed my coordinate system such that my integral is from minus pi to pi and not from minus pi over a to pi over a in here as well and in there as well. Now, of course, you can work out this integral and you would get to exactly the same result. It's just that this is, I think, a very intuitive and straightforward way to derive this result without having to go through these kind of integrations. And it's the physical kind of interpretation where you say, well, a Green's function tells you how you propagate in your system. If I now add a particle to the middle of an infinite chain, then I want to know how I can propagate in that, and I can see I can couple to my leads, and when I move here, then the Green's function of this is just given by how do you propagate it in this semi-infinite chain, and you then can just couple your Green's functions together to see what the propagation is for the full system. There are a few paths that you can take. If I go into A, I can just get out of A without ever going to the leads. I can go into A, I can move to the left and back and forward and back to A, or I can go into A, move to the right and back and forward and back to A. And of course you can do that infinitely many different ways. You can hop here, there, back and forward there, and back and forward there. And that's indeed what you just find when you do the full inversion. And that just tells you that you should be able, and you are able, to express the full Green's functions in terms of the Green's functions of the parts of the system. Thank you very much for your attention. In the next example, we'll have a look at not a local Green's function, but a non-local Green's function where you create a particle at one side and annihilate it at another side. And at that point, we'll see that the matrices here are no longer one-dimensional, but become two-dimensional. And then we're not able to just absorb the creation and annihilation operators that are above and below diffraction, because then there are really matrix inversions in there, instead of matrix inversions of a number that is 1. Thank you for your attention. We see each other later. Stay healthy.